Welcome to The Explainer. Today, we're going to demystify exactly how electric cars work. For over a century, we've basically relied on thousands of tiny, highly controlled explosions just to get from point A to point B. But right now, we're in the middle of a massive shift in automotive technology. We're trading those hot, complex explosions for a sleek, super efficient transfer of energy. So let's look under the hood and really break down the anatomy and mechanics of electric propulsion. So let's kick this off with a pretty fundamental question. What really happens when you just eliminate the internal combustion engine? When you literally strip away the gas tank, the spark plugs, the pistons, the entire exhaust system, what are you actually left with? Well, the answer is just beautiful simplicity. We're talking about electric traction motors that contain up to 90% fewer moving parts than a traditional combustion engine. 90%! Just think about that for a second. You're practically eliminating all that intense friction, the heavy mechanical wear and tear, and the massive amount of heat loss. Instead of thousands of stressed-out metal pieces grinding together, you just have this elegant, streamlined powertrain. Okay, so here's the blueprint for today's explainer. 1. The shift to electric. 2. The battery, our energy reservoir. 3. The powertrain, getting from battery to wheels. 4. Regenerative braking, how we recapture energy. And 5. Essential supporting components. Basically, we're going to track the literal commute of an electron from the exact moment it's stored all the way down to the wheels, and incredibly, back again. Let's jump right into section 1, the shift to electric. At its absolute core, an EV operates on a wonderfully simple principle of energy conversion. We're shifting away from burning fossil fuels to this incredibly clean, sustainable cycle. You're taking stored electrical energy, converting it into mechanical motion to spin your wheels, and then, and this is where it beats a gas car hands down, when you slow down, the vehicle can actually reverse that exact same process to recharge itself. It's just a brilliant, closed-loop dance of energy. Moving right along to the heart of a vehicle, section 2, the battery, your energy reservoir. You can basically think of the large traction battery pack as your fuel tank. Most EVs today use lithium-ion batteries. That's literally the exact same technology powering the smartphone or laptop you might be using right now, just, scaled up massively. Its capacity is measured in kilowatt-hours, or kWh. So just like a bigger gas tank holds more fuel and lets you drive further, a higher kilowatt-hour rating generally means a longer driving range for your EV. Now, here's where the internal chemistry gets really cool. This battery isn't just one big magic box. It's made up of hundreds, sometimes thousands of individual cells. When you're discharging, like when you're cruising down the highway, lithium ions commute in one direction, moving from the negative anode over to the positive cathode, and that releases energy to power the car. But then when you pull into your garage and plug it in, an external current forces those exact same ions to commute right back to the anode, packing that energy away for your next trip. All right, so the energy is successfully stored up, but how does it actually make the car move? Well, that brings us to section 3, the powertrain, battery to wheels. The exact millisecond you step on the accelerator pedal, a whole sequence of components springs to life. First up is the power electronic controller. You can think of this as the brains of the entire operation. It's constantly calculating and managing exactly how much electricity needs to flow from the battery to give you the speed and torque you're asking for, reacting in literal milliseconds to your foot. But we do run into a slight language barrier in our system here. Your battery stores electricity as direct current, or DC. But that main traction motor, it actually needs alternating current, or AC, to run at peak efficiency. So because your battery speaks DC, but your motor speaks AC, the inverter steps in. It acts as the ultimate translator, instantly converting the power so the energy just keeps flowing flawlessly. And that brilliantly illustrates the electron's commute we talked about earlier. Step 1. The battery dishes out that heavy-duty DC power. Step 2. The power flows straight through the inverter to be translated into AC. And step 3, that AC power fires up the electric traction motor, transforming that electrical energy directly into mechanical rotation. Now, getting that mechanical rotation to the wheels happens way differently than you might be used to. An internal combustion engine has a really narrow window where it operates efficiently. That's why a gas car absolutely desperately needs a complex, heavy, multi-speed transmission just to keep the engine from stalling out or over-revving. But an electric motor, it pumps out usable power across an incredibly wide range of speeds. Actually, scratch that, it's more like a massive wave of continuous power. Because of this, an EV usually just needs a super simple single-speed reducer to send the motor's high RPM directly to the wheels. And this engine of the EV gives you, the driver, a massive advantage. Whether they're using an asynchronous induction motor or a synchronous motor, the result is exactly the same. Instant torque right from a dead standstill. There's no waiting for fuel to pump, ignite, and build up pressure. You get immediate, thrillingly responsive acceleration the exact fraction of a second you even touch the pedal. Okay, let's move on to what I consider the real narrative climax of our explainer. Section 4, Regenerative Braking, Recapturing Energy. So in a conventional car, when you slam on the brakes, all of your forward momentum is entirely lost. It just burns off as heat through the brake pads. But in an EV, when you lift your foot off the accelerator, the car's computer tells the motor to stop pushing forward. Instead, the vehicle's kinetic momentum keeps the wheel spinning, which physically spins the motor. And by doing this, that whole process we just walked through is thrown into reverse. The motor stops consuming electricity and instead becomes a literal generator, using the car's own momentum to create electricity. The crucial takeaway here is that this ingenious software-controlled feature gives you two incredible benefits. First off, it shoves that newly generated electricity right back into your battery pack, physically extending your driving range while you're on the road. And second, because this magnetic resistance handles so much of the actual slowing down, it drastically cuts down on the physical wear and tear of your traditional friction brakes. That is going to save you a small fortune in maintenance over the life of the car. Before we completely wrap up our journey, we absolutely have to acknowledge the unsung heroes working behind the scenes. Section 5, Essential Supporting Components. These three components right here are absolutely vital for the EV to function in the real world. First, the onboard charger. It does the heavy lifting while you're parked, taking AC electricity from a standard wall outlet and converting it to DC to pack your battery full of energy. Next, the DC-DC converter. Remember, your main traction battery is incredibly high voltage, way too intense for standard electronics. So, this converter safely steps that huge voltage down to a normal 12-volt system, letting you run your headlights, wipers, and blast your infotainment system. Finally, the thermal management system. It's constantly heating and cooling everything. Batteries and electronics have a very strict Goldilocks temperature zone, and this system ensures they stay right in that sweet spot for maximum safety, high performance, and long-term battery life. So stepping back for a second, we've seen how this tech fundamentally replaces those old, heat-generating explosion engines. Instead of a messy mechanical beast, an electric vehicle is this elegant, highly efficient, software-controlled system of batteries, inverters, and motors. It's the cornerstone of modern, sustainable transportation, simply because it can consume energy for thrilling performance, and then seamlessly regenerate that energy to drive another mile. As we look toward the future of transportation and phasing out fossil fuels, this completely reframes what an automobile even is. Once you understand the hidden mechanics, it kind of leaves you wondering, next time you sit behind the wheel, are you just driving a car? Or are you piloting a highly efficient, software-controlled energy regenerator? Understanding this elegant journey of energy is going to change the way you think about driving forever. Thanks so much for joining me on this explainer, and keep questioning how the world around you actually works.